Welcome back, my dear students. In today's lesson, we will try to understand an electric dipole. What is an electric dipole, firstly? So, a system of two equal and opposite charges that are separated by a certain distance is called an electric dipole. For example, if you see at the diagram below, I have a minus q charge and a plus q charge which are separated by a distance of 2a. This is what an electric dipole looks like. Now, this distance 2a is generally called the length of the dipole, and it is represented by the vector 2a. Now, the direction of this electric dipole is always from the negative charge towards the positive charge. In practical life also, we come across a lot of electric dipoles. For example, the molecules of water, ammonia, they all are electric dipoles. How do I know that they are electric dipoles? It's because if you have any molecule where the atoms involved have some electronegativity difference, then there is a possibility that the centers of the positive and negative charges do not coincide. They are probably separated by some distance, and therefore they work like an electric dipole. Now, whenever we talk about an electric dipole, it's also very important to talk about the electric dipole moment. Electric dipole moment is represented by the letter P, and it's a vector quantity. It's defined as the product of charge times the length of the electric dipole. So P can be written as Q, where Q represents the charge on any of the dipole, and 2a is the length of your electric dipole. Now, charge is generally measured in coulombs. The length would be measured in meters. Therefore, the unit for electric dipole is coulomb meter. And the direction of your dipole moment is also from the negative to the positive. So, the dipole direction would go like this. Okay. Now, further talking about the electric dipole, so we have understood what is an electric dipole. How do we define the electric dipole moment for an electric dipole? The same way, we are going to talk about the electric field on the axial line of a dipole. So first, let's understand what is an axial line. So a line that passes through the centers of the two charges or the two charges that are involved in the electric dipole is called an axial line. So it is simply the line that passes through the centers of the two charges involved is called the axial line. So this line that you see over here, this one is my axial line. So I want to find out the electric field at a point P here on the axial line. So this is a point P, and I want to find the electric field on this point P due to this dipole along the axial line. So what I assume is that minus q and plus q are the two charges that are involved in the dipole. They are separated by a distance 2a. This point P is at a distance r. R is the distance of the point P from the center of the dipole. It is the distance of point P from the center of dipole. Keep that in mind. Now, if I talk about the negative charge here, we already know from our prior experience that for a negative charge, the field is always towards the charge. So this is the direction of the electric field due to the negative charge. It is supposed to be towards the charge. Therefore, you can see that the direction of the electric field due to the charge A is made towards left because it has to be towards the charge. For a positive charge, the direction of electric field is outwards. It's away from the charge. Therefore, the direction of electric field due to this charge, the positive charge at point B, is this way. It is towards right. Since the electric field due to the negative charge and the positive charge are in the opposite directions, therefore, when I will take the vector addition, I will have to take the directions also into account. So my electric field at this point P can be written as the electric field at point A plus the electric field at point B. But as we can see from here, the electric field due to the charge A is towards left and the electric field due to the charge B is towards right. So I will have to subtract these two. I'll have to take the electric field due to B minus the electric field due to A. By default, I'm taking the right side as positive and the left side as negative. Now that's up to you which one do you want to take. Now if I try to write the electric field due to the charge at B, so I can simply write it as K Q by the distance of this point B from the point B can be written as R minus A. This length over here can be denoted as R minus A. So electric field at point P due to the charge at B would be R minus A whole square. I am directly using the formula that the electric field due to a charge is given by KQ by R square, where R is the distance from the charge. So here the distance of point P from the charge is R minus A square. Now, apart from this, if I talk about the electric field due to this negative charge at A, then that one would be K times Q, and the distance of this A point from the point B would be R plus A. So this is R plus A whole square. Now from here, the electric field at point P can be written as, if I take KQ as common and just try to simplify this expression, this is R minus A whole square minus 1 upon R plus A whole square. I can take in the LCM and I would simply get R plus A whole square minus R minus A whole square. So this would become R square minus A square whole square. Now we can open this up by simply using the identities, or if you want to square it term by term, that is also possible. So if I simply open this, I'll have R square plus A square plus 2AR minus R square minus A square plus 2AR, and this whole divided by R square minus A square whole square. From here you can simply see that R square, A squares get cancelled and the 2AR and the 2AR become 4AR. So from here I can simply say that the electric field at this point P can be written as KQ into 4AR by R square minus A square whole square. Now from the definition of dipole moment, we know that P, which is the dipole moment, would be equal to 2AQ. So over here, this 4 can be split up as 2 into 2, and I have A and Q. So I can write this electric field in terms of the dipole moment, and it would become 2 times Kp upon R square minus A square whole square. So this is actually the electric field at point P, that is on the axial line of a dipole. From here, if I want to talk about the fact that if it is a small dipole, by small dipole I mean that the distance A is much less than R. If I take this condition and I apply this condition over here, then I can ignore this A square in the denominator, and my electric field over here would simply become 2kpr upon r to the power 4. So this r and this r get cancelled here. So my electric field finally can be written as 2kp by r cube. This is only applicable when you have a small dipole. If the distance A is not less than r, then you cannot use this. In fact, it has to be much less than r, then only we can use this. Here the direction of electric field is also, from the negative to the positive, which is the same as that of the dipole moment here. The electric field and this point, the dipole moment, they have the same direction. So the E axial is 2kp by r cube. I hope you understood this definition, this derivation. In case you have any questions regarding this derivation or any suggestions for me, please feel free to write in the comment box. Now moving further, let us talk about the electric field on the equatorial line of a dipole. Now for the equatorial line, what is this equatorial line? Equatorial line is the line that is perpendicular to the line passing through the centers of the dipole. To the line passing through the centers of the charges, you can also say. Now, in order to calculate this, you have to understand that let's say that our dipole is here. AB is my dipole. On A, I have put in the negative Q charge. On B, I have put in the positive Q charge, and they are separated by a distance of 2A. Again, I want to find out the electric field at this point P, which is at a distance R from the center. This angle here is 90 degrees, and if I can just assume this angle to be theta, then this angle over here would also be theta. If this is theta, this is also theta, and this is also theta. Now, electric field due to this negative Q charge would be towards the charge. Therefore, the direction of electric field due to this one is this way. It is towards the charge. For the positive charge, the direction of electric field is away from the charge. So, it is directed outwards like this along the vector M there. Now, I have two vectors which are inclined at an angle of theta with one another, or 2 theta from one another, and I want to find the resultant. So if I want to find the electric field at this point P, ideally I'm supposed to be calculating the vector addition of electric field due to A and electric field due to B. Now you can do the vector addition by using triangle law of vector addition, or you could simply take in the components. If I take the components of EB, then EB is inclined like this. So I can have EB sine theta and EB cos theta. Similarly, if you look at EA, I can take components of EA as well. EA is inclined here at an angle theta. So this side would be EA cos theta, and this side would be EA sine theta. Now if I want to write in just the magnitude of EA, then the magnitude of EA would be equal to KQ by the distance AP can be written as R square plus A square under the root. This is simply by using Pythagoras theorem. So distance AP and BP both are R square plus A square under the root. Therefore, the electric field due to the charge A would simply be R square plus A square. There is a square root and then I square it. So the square root and the square get cancelled. This is the magnitude. If I try to write the electric field due to the charge at B, then also I'll get the same magnitude. So magnitude of EA and EB is same. Now since the magnitudes are same, therefore the vertical components cancel out each other and only the horizontal components are left. Therefore, the electric field at point P can be written as 2 times EA cos theta. You can write EA cos theta plus EB cos theta, but then EA and EB are equal. So I've just written it as 2 times E cos theta. Now let's just substitute in here. So we have 2 times EA, which is simply KQ by R square. And then the value of cos theta. From this triangle, from the triangle AOP. In triangle AOP, if I want to write in the cos theta, then you can very easily see that my cos theta can be written as A upon R square plus A square. So the value of cos theta can be written as A upon R square plus A square to the power half, or you can put it under the root, that's your choice. So from here, if I just combine this, I get 2AQ times K upon R square plus A square to the power 3 by 2. The half and 1 become 3 by 2. And then we also know that 2AQ is nothing, but it's the dipole moment. So I take it as P. So from here, I can simply say that my EP is equal to K times P by R square plus A square to the power 3 by 2. This is my final expression for the electric field at a point P, which is on the equatorial line of the dipole. Now, in case it's a small dipole, so for a small dipole, we can simply say that if your A is much less than R, then this expression from here, if your A is small, then I can just ignore the A, then my EP becomes Kp by R cube, because R square times 3 by 2, so 2 and 2 get cancelled, so it is just R cube. Now this is applicable again only for a small dipole. So only for a small dipole, if you compare the electric field at the equatorial point and the axial point, then you can say that the electric field on the axial point is twice the electric field on the equatorial point. Now this is only applicable for a small dipole, otherwise this will not work. I hope this derivation also made sense to you. Now, further moving ahead, we are going to answer a very easy basic question. It's a formula based question, just direct substitution is involved. So it says that two charges of plus 25 into 10 to the power minus 9 coulombs and minus 25 into 10 to the power minus 9 coulombs are placed 6 meters apart. Find the electric field at a point 4 meters from the center of the electric dipole on the axial and the equatorial line. So we have two parts. Now they haven't told us that this is a dipole directly, but you can see that the two charges are equal and opposite and they are separated by some distance. So it is a dipole. Further, over here, if I just talk about the first part in here, now for the axial line, we have just derived the formula. Now this is not a small dipole, because you can see the 6 meters and 4 meters are pretty much comparable, so it's not a small dipole, and they have not also told us that it's a small dipole, so we cannot use the small dipole formula. So electric field on the axial line is simply given by K times 2PR. I'm using the complete formula, R square minus A square and whole square. So we will just make all the substitutions here. So the value of K is 9 into 10 to the power 9. The dipole moment is 2AQ, you know that. So this would be 2 times 2A, and the distance 2A is given to us as 6. And the charge is given to us as 25 into 10 to the power negative 9. And R, which has a distance of 4 meters, upon, you have 4 square minus 6 square, no, not 6 square, sorry, 3 square, because 2A is 6, so A would be 3. So this is 3 square and whole square. Now if you will just substitute here and just simply calculate, then by putting it on the calculator, I get this value as approximately 55.1 Newton per coulomb. So that's my electric field on the axial point. Similarly, I can find it for the equatorial line. So electric field on the equatorial line is given by Kp by R square plus A square to the power 3 by 2. So the electric field on the equatorial line, the value of K is 9 into 10 to the power 9 again. For the dipole moment, I have to do 2A into Q. So 2A is given to me as 6 and Q is again 25 into 10 to the power minus 9 upon my R over here is 4. So 4 square, and A is 3. So 3 square into 3 by 2. Now when I calculate this value, again this value comes out to be 10.8 newtons per coulomb. So you can see from here it's not exactly half, it's not even exactly 1/4 of it. So here using the formula which was approximated for a small dipole will definitely not work. So that's something that you have to be very careful with. So I hope you understood this question as well. Further, let us talk about the electric dipole in a uniform electric field. So I have a dipole AB, which is minus Q and plus Q, separated by a distance 2A, and there is an electric field E which is making an angle theta with the dipole over here. So if I want to find out the fold, like what happens over here when you put a dipole in an electric field, so let us try and analyze that. So first let's talk about the force. If I talk about the force at the point A, then that is simply given by minus QE, and the force at point B is simply given to me as plus QE. Now if you look in carefully, both of these forces, since they are equal and opposite in direction, they will cancel out each other. So the net force on a dipole is 0 when kept in a uniform electric field. But what about the torque? Is the torque 0? So to answer that, this dipole or this force will make it rotate in the clockwise direction, and this dipole, like this force over here, will also make it rotate in the clockwise direction. Since both the torque due to both of them is in the clockwise direction, therefore the net torque will not be equal to 0. To calculate the torque, you can see torque is simply force times the perpendicular distance between the center or between the pivot point and the charge. So over here, or the force basically. So over here, if I write the torque due to both of these, if I write it due to the charge A, then the force due to charge A is QE. And if I take the perpendicular distance, then I have to take in this distance here, since that is the perpendicular distance. This is also theta, so this distance here would be A sine theta. For this dipole also, I'll have to take in this distance, that is again A sine theta. So over here I'll have QE into A sine theta plus, due to the charge B, again it is QE and the distance is A sine theta. Why am I adding the two torques? Because both of them are in the clockwise direction. So from here I get torque as, so this becomes 2AQ times E sine theta. Now 2AQ is nothing but the dipole moment, so I can write it as PE sine theta, or it can be written as torque is the cross product of dipole moment and the electric field E. So torque is equal to P cross E. Okay, this is a small derivation. It comes for 2 marks generally, but it has a lot of significance here in understanding it. For example, if you look in carefully, over here, as I told you earlier, that the net force on the dipole is 0. Secondly, if the torque on the dipole becomes 0, like if the P and E, if the dipole moment and the electric field become parallel to each other, that means my theta would be 0 degrees, and then that will imply my torque is 0. On the other hand, if my P is perpendicular to the electric field, then my theta would be 90 degrees, and that time my torque would be maximum. This is maximum torque here, which would be equal to simply PE, and this one is 0. So these two conditions, that if your dipole moment and electric field align themselves, and that gives you a 0 torque, but if the dipole moment and the electric field are perpendicular to one another, they will give you the maximum possible torque, which is equal to PE. Okay, so that's all about the electric dipole in a uniform electric field. Now let us move on to another question. So it says that an electric dipole with electric dipole moment 4 into 10 to the power minus 9 coulomb meter is aligned at 30 degrees. So they have told us that electric dipole moment here is 4 into 10 to the power minus 9 coulomb meter. It makes an angle of 30 degrees here, and the direction of electric field over here, like the value of electric field, is 5 into 10 to the power 4 newtons per coulomb. We have to find the magnitude of the torque. So we know that torque is simply going to be PE sine theta. So let's just simply substitute. So P is 4 into 10 to the power negative 9, and electric field is 5 into 10 to the power 4. Sine theta is sine 30, and sine 30 we know is half. So the answer from here becomes 4 into 10 to the power minus 9 into 5 into 10 to the power 4 and into a half, which I can cancel out here. So 2 times 5, that's a 10, and this is 10 to the power minus 5. So my torque from here becomes 10 to the power negative 4. The unit for torque would be Newton per meter, because you're simply doing force times the distance. So this is Newton meter. And with this, we have discussed almost everything related to an electric dipole. Its electric field, how it behaves when we keep it in a uniform electric field, all the derivations, and the relevant questions. So I hope you understood and you enjoyed the video. If you liked the video, if you understood the concept, then please do not forget to subscribe and like. Also, I would be very happy if you leave a comment for the video.